Class 11, Chapter 10, that is Mechanical Properties of Fluids. Mechanical Properties of Fluids. Mechanical Properties of Fluids. Okay, then let's start this chapter, Chapter 10 of Class 11 Physics. Let's see the topics: pressure, streamline flow, Bernoulli's principle, viscosity, surface tension. Those are the topics here. Now let's start off with introduction here. 10.1 Introduction. Mechanical properties of fluids. In this chapter we shall study some common physical properties of liquids and gases. Liquids and gases can flow and are therefore called fluids. Okay, what they are saying here, what we are going to see is study in this chapter is common physical properties of liquids and gases. Fluids are things which can flow. So because liquids and gases can flow, they're called as fluids. Fluids doesn't solely mean liquids, it also constitutes gases as well. Whatever substance which can flow are called as fluid, and liquids and gases can flow, so they are called as fluids. It is this property that distinguishes liquids and gases from solids in a basic way. We can say that water is flowing, or a gas is flowing, or wind is flowing, or wind is breezing, but we cannot say a rock is flowing or a iron is flowing. We cannot say that. This is the most well-known property that distinguishes liquids and gases from solids in the most basic way. Fluids are everywhere around us. Earth has an envelope of air, and two-thirds of its surface is covered with water. Basically, Earth has atmosphere, which is an envelope of air. We are currently in a fluid right now in the atmosphere, and there is also water, which constitutes 70% of the Earth. Water is not only necessary for our existence. Every mammalian body constitutes of mostly water. All the process occurring in living beings, including plants, are mediated by fluids. It may be photosynthesis, which needs gases, liquids, water, carbon dioxide, etc. It's mediated by fluids. Thus, understanding the behavior and properties of fluids is important. Because of all these reasons, we need to understand the behavior and properties of fluids for a comfortable life. How are fluids different from solids? First common difference we saw: fluids flow, solids don't flow. What is common in liquids and gases? Unlike a solid, a fluid has no definite shape of its own. Solids and liquids have fixed volume, whereas a gas fills the entire volume of its container. We have learned in the previous chapter that the volume of solids can be changed by stress. Okay, before continuing, let's see what they're saying here first. What is common in liquid and gases, they asked. They are made up of matter. All the gas, liquid, fluid, all are made up of matter, where matter is constituent of atoms. That is a common thing. And specific properties of solid has a fixed shape and fixed volume, whereas gas doesn't have a fixed shape but it has a fixed volume. But gas, if we take it, neither has a fixed shape nor a fixed volume, because if we take a gas and fill it in a a small container and a big container, it will occupy both the whole of the both containers, even though if we fill the same amount of gas in both the containers. So in such a case, we can say that solid has fixed shape and fixed volume. Liquid doesn't have fixed shape but has fixed volume. It doesn't have fixed shape because any beaker we add liquid into, the liquid will take the shape of the beaker, so it doesn't have fixed shape. but it has fixed volume. It does not completely occupy the containers or the beakers. Because of that, it has a fixed volume. As for gases, they have neither fixed volume nor fixed shape. Okay, and they are saying that in previous chapter, mechanical properties of solids, we saw that under hydraulic press, when we immerse an object in water, the stress will be equal and into the center, or it will be same in all parts of the surface. Because of that, the 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 solid will get compressed, but there will be no change in shape. The volume will reduce. The volume of solid, liquid, or gas depends on the stress or pressure acting on it. Important to remember here or understand, the volume of a solid, liquid, or gas depends on the stress or pressure acting on it. No matter the volume, no matter the state of matter, that is solid, liquid, or gas, the property of volume of these substances depends on stress or pressure acting on it. We saw that gas doesn't have fixed volume, liquid and solid do, but even solid, when uh, under some stress like hydraulic stress, the volume will change there. The volume will still change there. Because of that, we can understand that the volume of solid, liquid, or gas, it depends not only on the state of matter but also on the stress or pressure acting on it. When we talk about fixed volume of solid or liquid, we mean its volume under atmospheric pressure only. Under atmospheric pressure, we see that solid or liquid have a fixed volume. If we increase or decrease the pressure, they may change in volume. The difference between gases and solids or liquids is that for solids or liquids, the change in volume due to change of external pressure is rather small. Basically, gases, after understanding that this solid, liquid having fixed volume only in atmospheric pressure, we can say that the difference between gases, solids, and liquids is that uh, gas, it does in atmospheric pressure itself, it has a large change in volume, or even for small change in pressure there is a large change in volume. But liquids and solids show much lower change in volume for change in pressure. So because of that, even though they change in volume, it is harder to notice. In other words, solids and liquids have much lower compressibility as compared to gases. Shear stress can change the shape of a solid, keeping its volume fixed. The key property of solids is that they offer very little resistance to shear stress. Their shape changes by application of very small shear stress. The shearing stress of fluids is about a million times smaller than that of solids. Okay, what they are saying is that shear stress is basically the stress, like when the force is applied, when you have two surfaces and we apply force parallel to the two surfaces, then this kind of stress is called as shear force or shear stress, where we take force, the parallel acting force, the force acting parallel to the surface of the object by area of the surface, we call it as shear stress. And the key property of fluids, okay, one more thing before that, shear stress can change the shape of an object like solid, keeping its volume fixed. The volume will change or decrease in cases like hydraulic stress, not shear stress. The shear stress can change the shape but keep its volume fixed. Now, the key property of fluids is that they offer very little resistance to shear stress, meaning what that means is that We can change the shape, but the volume will remain constant. That is the reason, that is the sole reason why, uh, based on this key property, we can understand that why, like when we pour liquid into a beaker, it will take the shape of the beaker. That is because it is very little resistance to shear stress. It is offering very little resistance to shear stress. Because of that, because we are not changing any kind of volume here, the any change in shape which comes under shear stress, and fluids which can occupy and take the shape of any kind of container they are placed in, we can understand that they have very low resistance to shear stress. That is the reason they change shape so easily. The shape changes by application of very small shear stress. The shear stress of fluids is about a million times, 10 power 6 times smaller than that of solids. Okay, that's with the introduction here. Let's go to the first topic, that is pressure. A sharp needle, when pressed against our skin, pierces it. Our skin, however, remains intact when a blunt object with a wider contact area, say the back of a spoon, is pressed against it with the same force. Okay, basically, when we take a sharp needle and a spoon, and when we press it against our hand with the same amount of force, then if we ask the question which will pierce our skin, which will go into our skin, then obviously the answer will come out to be the needle, not the spoon. Okay, let's continue reading to understand why so. If an elephant were to step on a man's chest, his ribs would crack. His ribs would crack. A circus performer across whose chest a large, light but strong wooden plank is placed first is saved from this accident. Okay, basically, another example is, if we see an elephant, if this elephant were to step on a man's chest, obviously the ribs would crack. But in circus, some people perform the same feat where an elephant steps on their chest, but their ribs won't crack. There will be no damage to them because they use a large, light, and strong wooden plank over their chest before the elephant steps on them. And he is saved from the accident. Why so? Let's see. Such everyday experiences convince us that both the force and its coverage area are important. Both the force and its coverage area, how much it is covering. Smaller the area on which the force acts, greater is the impact. The smaller the area the force acts, the greater the impact. And this impact is known as pressure. When an object is submerged in a fluid at rest, the fluid exerts a force on its surface. This force is always normal to the object surface. Let's see that again. When an object is submerged in a fluid at rest, the fluid exerts a force on its surface, that is the object surface. This force is always normal to the object surface. Okay, basically it means it's always perpendicular to the object surface in case of a fluid. This is so because if there were a component of force parallel to the surface, the object will also exert a force on the fluid parallel to it as a consequence of Newton's third law. This force will cause the fluid to flow parallel to the surface. Since the fluid is at rest, this cannot happen. Okay, why we say that the pressure, the force will always be normal to the surface of the object is because, let's assume there is a component which is parallel to the surface of the object. There, when we resolute, let's say there is a there's a pressure or force which is parallel to the surface. In such a case, the due to Newton's third law of motion, not motion, Newton's third law, when the water exerts a parallel force on the object will also exert an opposite and equal force on the water. Because of that, the water needs to flow, that is parallel to the surface. But because the water is at rest, we cannot see that happening. And because of that, we conclude that the parallel component of the force does not exist. Hence, the force exerted by the fluid at rest has to be perpendicular to the surface in contact with it. This is shown in figure 10.1a. A force exerted by the fluid in the beaker on submerged object or on the walls is normal perpendicular to the surface at all points. This doesn't only refer to the wall or the sides of a object, but also the walls of the container as well. It will always be perpendicular like this, 90-degree angle. Let's come back here. The normal force exerted by the fluid at a point may be measured. An idealized form of one such pressure measuring device is shown in figure 10.1b. It consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. This device is placed at a point inside the fluid. The inward force exerted by the fluid on the piston is balanced by the outward spring force and is thereby measured. Okay, let's read that again. The normal force exerted by the fluid at a point may be measured. For the force, if we want to measure the force by the fluid at a point, we want to measure a force exerted by the fluid at a point, then we use an idealized pressure measuring meter. It's pressure measuring meter, not an idealized one. This is just for showing here. It's not completely the same. Pressure measuring device. Now this pressure measuring device consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. This device is placed inside a point at this placed at a point inside the fluid. The inward force exerted by the fluid on the piston is balanced by the outward spring force and is thereby measured. Basically, we keep this spring. There is a piston here. The piston is connected to a spring and there is a vacuum here. There is no resistance. Why we do keep a vacuum there is because there should be no resistance. There should be no air resistance and all. When we keep it inside, there will be a force acting on this piston and it will get pushed down, and based on how much extent the piston was pushed down, we can calculate the force acting at that point. That is what they're saying. An idealized device for measuring pressure. Okay, if F is the magnitude of this normal force on the piston of area A, the average pressure is defined by the normal force acting per unit area. Let's read that again. If F is the magnitude of this normal force on the piston of area A, okay, they're saying F is the magnitude or total force acting normal to the piston, this surface, acting normal to this surface, that is F. This area of this piston is denoted by A. If so, then the average pressure, that is PAV, is defined as the normal force acting per unit area. Force acting per unit area is defined as pressure, where STP means standard temperature and pressure. There is an extra information given. STP means standard temperature and pressure, 0 degrees and 1 atm pressure. 0 degrees and 1 atm pressure. Pressure average is equals to force by area. In the principle, the piston area can be made arbitrarily small. The pressure is then defined in a limiting sense as pressure, which is equals to limit delta A reaches 0, delta F by delta A. The pressure is a scalar quantity. We remind the reader that it is the component of the force normal to the area under consideration and not the vector force that appears in the numerator in equations 10.1 and 10.2. Its dimensions are ml t power minus 2. The unit of pressure is Newton per meter square. It has been named as Pascal in honor of the French scientist Blaise Pascal 1623 to 1662, who carried out pioneering studies on fluid pressure. A common unit of pressure is the atmosphere, that is ATM, that the pressure exerted by the atmosphere at sea level is equals to 1 atm, which is equals to 1.013 into 10 power 5 Pascal. Another quantity that is indispensable. Okay, before that, let's understand what they have given here. We already know that pressure is the force, the impact of force depend based on the coverage of area. The total impact of force based on coverage of area is known as pressure. So the lower the area, the higher the pressure. So if we consider the piston area can be made arbitrarily small. If we reduce the area of the piston, basically we are reducing the area of the piston surface area, we are reducing it and making it very small, where then if we use differentiation formula, P which is equals to limit delta A which is reaching 0 and delta F by delta A. And here we can see that pressure is a scalar quantity. It is the force, it is a force acting normal to the surface. No matter what kind of pressure it may be, it is a scalar quantity and it is a force acting normal to the surface area. It is needed that it is the force acting normal to the surface of the piston or surface of any kind of object. It is a component of the force normal to the area under consideration and not the vector force that appears in the numerator, that is force. Its dimensions are ml t power minus 2 and SI unit is Newton per meter square or Pascal, and atmospheric pressure at sea level is approximately 10 power 5 Pascal. Another quantity that is indispensable in describing fluids is the density rho for a fluid of mass m occupying a volume v. One of the other important things we need to know for measuring the uh, or not measuring the pressure, but for describing fluids, very important quantity that is useful for describing different fluids is the density of that fluid. It is denoted by rho, which looks like a small p here, that's called a rho, and this quantity is it's a indispensable for describing the different various fluids. Density of a fluid, density formula which is equals to mass by volume. The dimensions of density are ml power minus 3. Its SI unit is kg per meter cube. It's a positive scalar quantity. A liquid is largely incompressible and its density is therefore nearly constant at all pressures. Okay, let's see what they said again. A liquid which is largely incompressible. Normally, a liquid which is very hard to compress, and mostly its density will remain constant at all pressure, but because at most of high varying pressure it does not change in density much. Because of that, we can assume that its density is constant. Gases, on the other hand, exhibit a large variation in densities with pressure. Even though liquids which do not get compressed much even under changes in pressure, but gases, even with small changes in pressure, change in densities large, like there will be large changes in density. The density of water at 4 degrees is 277 Kelvin, is 10 power 3 kg per meter cube. The relative density of a substance is the ratio of its density to the density of water at 4 degrees centigrade. Okay. The density of water at 4 degrees centigrade. This is the densest part of water, densest the water at 4 degrees temperature, the water will be at its densest state. This can be seen as anomalous behavior of water, where from higher temperature till 4 degrees centigrade, the water will continually increase in increase in density. Basically, it will contract. But from 4 degrees to 0 degrees, it will rapidly expand in the ice form. This is the anomalous behavior of water, which we will see later in thermal properties of matter later. For now, the density of water at 4 degrees centigrade or 277 Kelvin is used as a standard, and it is equals to 10 power 3 kg per meter cube. And based on this standard of water, we define a relative density of a substance, and this relative density is a ratio of the object's density per the density of water at 4 degrees. This relative density is dimensionless because obviously density by density, the dimensions get cancelled and it will be dimensionless. It is a dimensionless relative density is a dimensionless positive scalar quantity defined by the density of the substance by the density of the water at 4 degrees. For example, the relative density of aluminium is 2.7. Its density is 2.7 into 10 power 3 kg per meter cube. The basically they give another example here. Relative density of aluminium is 2.7 and density of the aluminium is 2.7 into 10 power 3. And knowing the relation between density and relative density, we can find out one if the other is not given, where the constant values are the density of water, which will not change, and the relative density or the density of the substance which is given, through which we can find out either relative density or the density of the substance. The densities of some common fluids are displayed in table 10.1, where water has a density of 10 power 3 and seawater. I'll Okay, then the break is over. Let's continue. Some values of densities of some common fluids are given here. Water being 10 power 3 kg per meter cube, sea water being slightly higher than normal water, mercury 13.6 into 10 power 3, ethyl alcohol 0.806, which is lesser than water. The blood is higher, the density of blood is slightly higher than water. Air, which is very very less compared to water. When water is in 10 compared to it is 10 power 3, air is only in the one single digits. Hydrogen, with hydrogen density of hydrogen being even lesser, being in 10 power minus 2, 9 into 10 power minus 2, which is basically 10 power minus 1 approximately. And if we consider interstellar space, it will be around 10 power minus 20 kg per meter cube. Densities of some common fluids at STP, as standard temperature and pressure, that is 1 atm pressure and 0 degrees temperature. Let's see an example. The two thigh bones, femurs, each of cross section area 10 centimeter square, support the upper part of a human body of mass 40 kg. Estimate the average pressure sustained by the femurs. Okay, they gave two thigh bones, each of cross section area 10 centimeter square, support the upper part of a human body of mass 40 kg. Now we estimate the average pressure sustained by the femurs. Average pressure, we already know the formula. It is F by A. And since it is two femurs, we divide the force into two. The force, which is equals to the weight of the person, we divide it into two. That is 40, 20 kgs. No, right. They did not ask the pressure on each femurs, but they collectively said as sustained by the femur. So we don't need to separate it. Force by area, which is equals to 2 into 10 pi r square basically. They already gave the area. We don't need to calculate it, 10 centimeter square. But since we have two femurs, it will be 2 times 10 centimeter square. Okay, then let's see the solution. Total cross sectional area of the femur is 2 into 10 power 10 centimeter square of including both the femurs. We can write it as in terms of meter, 20 into 10 power minus 4 meter square. The force acting on the femurs is 40 kg weight or 400 newton, taking g which is equals to 10 meter per second square. The force acting vertically down, the force is acting vertically down and hence normally on the femurs. Thus the average, which is equals to PAV, which is equals to F by A. If we take the value as F, which is equal to 400, and area, which is equals to 20 into 10 power minus 4, we will get the final value to be around 2 into 10 power 5 Newton meter square. Okay, now coming to the subtopic, that is Pascal's law. Subtopic under the main topic, pressure. Pascal's law. 2.1, 10.2.1. The French scientist Blaise Pascal observed that the pressure in a fluid at rest is the same at all points if they are at the same height. This fact may be demonstrated in a simple way. Okay, let's let's just see what he said again once more. What Pascal said, the scientist Blaise Pascal said is that pressure in a fluid, that is pressure in a fluid at rest, it's not moving, it's in state of equilibrium, it's in rest, is same at all points if they are at the same height. If they are at the same height, the pressure is same at all points. Now let's see how this can be proved in a simple way. Proof of Pascal's law. ABC dash dBf dEf is an element of the interior of a fluid at rest. This element is in the form of a right-angled prism. The element is small so that the effect of gravity can be ignored, but it has been enlarged for the sake of clarity. Okay, what they are saying is this is a prism like object, basically a triangle, but it has depth also. It's not a 2D shape but a 3D shape. It is a kind of a prism, and it is a right angled prism. It is very small, but for us to understand, it is enlarged. Because it is very small, the water in this area is very small, very mass is neglected, so gravity is also neglected. Now let's see the proof. This figure shows an element in the interior of a fluid at rest. This element, that is ABCDEF, is in the form of a right angled prism. In principle, this prismatic element is very small so that every part of it can be considered at the same depth, meaning they are at the same depth of the beaker, same height of the beaker. Because it's considered to be very small, the length of BA or BC doesn't matter. They're all very negligible. Same depth, they can be considered to be at the same depth from the liquid surface, and therefore the effect of gravity is the same at all these points. But for clarity, we have enlarged this element. The forces on this element are those exerted by the rest of the fluid, and they must be normally to the surfaces of the elements as discussed above. Because we ignore gravity, the only force experienced by this part of a fluid is the pressure due to other parts of the surrounding fluids. And we already know that for any surface, the pressure must be normal to the surface. Thus, the fluids exerts pressure PA, PB, and PC on the on this element of area corresponding to the normal forces FA, FB, and FC as shown in figure 10.2 on the faces BEFC, ADFC, and ADEB, denoted by AA, AB, and AC respectively. Okay, let's read that again. If we see that the only force they experience is the pressure due to the surrounding molecules, and if we consider them as phases, ADBE phase, ADCF phase, BC phase, BCFE phase, considering all of these phases, the forces, let's assume them to be FA, FB, and FC, and the pressure being PA, PB, and PC, and pressure which is equal to force by area. Now we consider the area of the respective phases. Considering them, we have here FB sine theta which is equals to FC, F is FB sine theta which is equals to FC, and FB cos theta which is equals to FA, that is by equilibrium, AB sine theta which is equals to AC, and AB cos theta which is equals to AA by geometry. Okay, by equilibrium, let's see the forces by equilibrium first. Why it is so is because if we consider the forces, then if this is an angle, this is the normal, this is the angle with the normal, and if we draw another face like this, is the force resolution of the forces. Taking angle theta here instead of here, we can write this as sine theta, and FB sine theta is equals to FA FC dash. Wait, considering this part, this force here, or considering the angle here itself, considering the angle theta here itself, we can write this as F sine theta, and FC which is equals to, because they are in equilibrium, FC which is equals to F FB sine theta. FB sine theta, FB sine theta which is equals to FC, and one more force, FB cos theta which is equals to FA. We can see by equilibrium, and coming to area by geometry, AB sine theta, AB sine theta which is equals to AC, and AB cos theta which is equals to AA. Because of that, FB by AB which is equals to FC by AC, FA by AA. They just equated sine theta here, where sine theta is equals to FB by FC, and sine theta is also equals to AB by AC, through which we will get FB by AB which is equals to FC by AC which is equals to FA by A, where PB which is equals to PC which is equals to PA. Hence, pressure exerted is same in all directions in a fluid at rest. It again reminds us that, like other types of stress, pressure is not a vector quantity. No direction can be assigned to it. The force against any area within or bounding a fluid at rest and under pressure is normal to the area regardless of the orientation of the area. Now consider a fluid element in the form of a horizontal bar of uniform cross section. The bar is in equilibrium. The horizontal force exerted at its two ends must be balanced, or the pressure at the two ends should be equal. Okay. Before going further, what they are saying here is the pressure exerted at all points in a fluid will be at rest. A fluid at rest will be same. The pressure exerted is same in all directions. The fluid at rest is same at all directions in fluid at rest, and pressure is not a vector quantity. No direction can be assigned to it. The force against any area, like that can be the any area like of an object which is inside the water or bounding the water like the container, the pressure will always be normal to it regardless of the orientation of the object or the container. Now, next paragraph, if we consider a fluid element in the form of a horizontal bar of uniform cross section. Okay, same thing. Here we imagined or considered a element of right angled prism. But instead of that, if we consider a horizontal bar of uniform cross section, then the bar is in equilibrium. The horizontal forces exerted at its two ends must be balanced, or the pressure at the two ends must be equal. Okay, the horizontal forces acting at its two ends must be balanced. If we consider a fluid element in the form of a horizontal bar and it's having a uniform cross section, the bar is in equilibrium. The horizontal force exerted at its two ends must be balanced, or the pressure at its two ends should be equal. This proves that for a liquid in equilibrium, the pressure is same at all points in a horizontal plane. Suppose the pressure were not equal in different parts of the fluid, then there would be a flow, as the fluid will have some net force acting on it. Hence, the absence of flow, the pressure in fluid must be same everywhere in a horizontal plane. Basically, same thing. They are using another form to say it. If the pressure was not equal, meaning there is a net force acting on it. If if pressure is equal, that means net force is zero. But if the pressure is not equal, then that means there is a net force acting on it. And basically what that means is, if we consider the same thing here, okay, if the pressure is not equal at every point, pressure is basically due to force is resulting in pressure. So let's just say force, let's consider force itself. Force is acting like this, all these directions. If this force is not equal, meaning the force acting on this surface is not equal to this surface, then obviously if we resolute of all of them, both of them, then the net force we will get would not be zero. If the net force, let's assume this force is larger, then the net force should be acting in this direction. If so, this part of this water should be moving in that direction. There should be flow of these particles. But if we have a stable water which is at rest, we can assume that there is no net force acting in this direction or any kind of direction due to unequal forces. Because there is no movement in any kind of direction, because a water at rest is possible, we can assume that pressure is equal. And we specifically say this for water at rest because that is the sole reason we are defining it. We can define pressure is equal using this, one of the main reasons. As one of the main reasons, it is the pressure is equal because there is no motion. If there is motion, if the part if the fluid is under motion, there may be other conditions. Okay, let's go to the next subtopic under pressure. Variations of pressure with depth. How the pressure will vary with depth. Consider a fluid at rest in a container. In figure 10.31 is at a height h. Okay, let's see the diagram first. Okay, fluid under gravity. The effect of gravity is illustrated through pressure, a vertical cylindrical column. This is a cylinder containing, this whole thing is a container containing water, and we consider a cylindrical element of the water here, a cylindrical element here, and this element is in perfect equilibrium because there is no motion of water. The water inside the container is at rest, so this cylindrical object must that must mean that the water we consider, the water we considered a part of this cylindrical element must also be at rest or equilibrium. And the force, this is not negligible here. This water does is not negligible. In the right angled prism above, we took negligible mass, so gravity we ignored. But here we are not going to ignore gravity here. This water element is of considerable mass. It has, this cylinder has a height h, area a, radius r, and force mg acting downward to it and pressure acting on its surfaces. Let's consider a point at rest in a container in figure 10.3.1 at height h above a point 2. The pressure at points 1 and 2 are P1 and P2 respectively. Okay. In the pressure at points 1 and 2 are P1 and P2. Okay, then let's continue. This is point 1 and this is point 2. This is the height of the cylinder here. The pressure at first surface is P1 and second surface is P2. Now consider a cylindrical element of fluid having area of base A and height h. As the fluid is at rest, the resultant horizontal forces should be zero and the resultant vertical forces should balance the weight of the element. Okay, because we know that the fluid is at rest, that must mean the net force should be zero and it should be balanced by the uh, mg, that is the gravitational force acting on it. The forces acting in the vertical direction are due to the fluid pressure at the top, that is P1A. The forces acting in the vertical direction are due to the fluid pressure at the top. Let's read that again. The forces which is acting in the vertical direction are due to the fluid pressure at top, that is PA, acting downward at the bottom, P2A, acting upward. If mg is the weight of the fluid in the cylinder, we have P2 minus P1A is equals to mg. Okay, it's kind of confusing, but let me clarify it. Here we consider a cylinder. It is a part of the water. We just consider the water to be forming in the shape of a cylinder. Now, this cylinder, like water element, has certain mass. Let's consider it as a m. Due to this, it experiences a force downward due to gravity. That is, let's call it as mg. Now, at the top surface here, there is forces acting on it. The force acting downward. Let's consider this forces P1A, where P1 is the pressure on that surface and A is the area of the surface. How this came to be is pressure which is equals to force by area and force which is equals to pressure into area. That is what we got here. Now if we do a free body diagram, this is the particle. There are two forces acting downward, that is mg, as well as the total average pressure area, that is the total average force acting downwards, P1A. Now there are also forces acting upward, and these forces are also due to pressure, and we will consider it as the pressure of second surface area. Because it's a cylinder, both the area will be same. Let's consider it as 1. The only force acting upward here is P1A. I mean not P1A, P2A. Same way, force which is equals to pressure into area. Free body diagram is drawn using forces. Now We know that this body, this cylinder, is in equilibrium. The water is at rest. So we can equate both the forces. We can say P2A is upward force, which is equals to, in magnitude terms, which is equals to P1A plus mg. Now rewriting this, we can write it as shifting this side, P2 minus P1, we take A out common, which is equals to mg. This is the formula they showed here. And as for the sideways forces, these forces shown here, if we see there are forces, there should be forces acting even in this direction. But because the forces are acting like this, they are equal and opposite in magnitude. Because of that, they get cancelled out. That this is the equation, P2 minus P1 A, which is equals to mg. Now if rho is the mass density of the fluid, we have the mass of the fluid to be rho v, which is equals to rho height into area, so that we get P2 minus P1, which is equals to rho gh. Basically they have mass. But if we consider, it is hard to measure the mass of the water, mass of the element of water that is inside the total water. It's hard to take out the specific amount of water and measure it. That is hard to do. Because of that, we use density formula. Density which is equals to mass by volume, and mass which is equals to density times volume, through which we will get mass. And volume for a cylinder, we can write as height times area. Is the same, we will substitute, we will get a mass which is equals to rho ha. Now substituting P2 minus P1 A, which is equals to rho gh a cancel, we will get P2 minus P1, which is equals to rho gh. This is one of the main formulas here, which is very important to remember. Okay, then let's continue. Pressure difference depends on the vertical distance h between. Okay, before that, let's observe the formula more. P2 minus P1, we can write it as the formula, we can write as pressure difference, which is equals to rho gh. And based on this, the pressure difference is directly proportional to height, and it is also directly proportional to density. The higher the higher the um, higher the distance between the surfaces which we are measuring pressure difference, the higher the pressure difference. This h is a difference between the two surfaces of which we are actually measuring the pressure difference. So the higher the distance between the, or higher the depth, the higher the pressure. If we observe, P2 is much greater than P1, so we can say as we go down, as the depth increases, the pressure will also increase. Okay. Okay, that's done. Okay, then let's go. The pressure difference depends on the vertical distance h between the points 1 and 2, mass density of the fluid, that is rho, and the acceleration due to gravity. If the point 1 under discussion is shifted to the top of the fluid, say water, which is open to atmosphere, Pi may be replaced by atmosphere pressure, Pa, and we replace P2 by P, then equation 10.6 gives P, which is equals to Pa plus rho gh. Okay. Another form of the above equation, that is difference between pressure, is, if we take, let's just say that the top of this fluid is exposed to air, which is exposed to atmosphere, then P1 we can write it as atmospheric pressure. This we are calculating is, this is atmospheric pressure. It can be, P1 can be replaced by atmospheric pressure, which is significantly lesser than the actual inside water pressure. P, which is equals to PA plus rho GH. We just sent P1 or PA from left to right. Thus, the pressure P at depth below the surface of liquid open to atmosphere is greater than atmospheric pressure by an amount rho GH. We can understand this equation by saying that the pressure inside the liquid is is greater than the pressure outside the liquid by a sum of, or by a constant, by a number of rho GH. The excess of pressure P minus PA at depth H is called gauge pressure. At that point, the area of cylinder is not appearing in the expression of absolute pressure. Thus, the height of the fluid column is important and not the cross-sectional or base area of the shape of the container. What matters is the depth of the fluid or height of the cylinder we are taking. What does not matter is the area of the cylinder, which gets cancelled out. It does not matter. No matter the area of the cylinder, the pressure difference will remain same. And even the shape of the container, size of the container also doesn't matter when we are considering a fluid element inside. What is gauge pressure? The excess pressure, basically the difference between P minus PA. How much more the pressure is compared to atmospheric pressure inside the liquid. That is called as gauge pressure. The liquid pressure is the same at all points at the same horizontal level, same depth, same depth. The result is appreciated through the example of a hydrostatic paradox. Okay, what they are saying is the liquid pressure is same at all points at the same horizontal level. When we consider the same horizontal level, the liquid pressure is the same at all points in the same horizontal level, that is same depth. Now we can appreciate this through an example of hydrostatic paradox. Consider, if we consider three vessels of A, B, C, if we see the vessels here, let me erase this. These are the three vessels. Illustration of a hydrostatic paradox. The three vessels A, B, and C contain different amounts of height, amounts of liquid, but all up to the same height. Consider three vessels ABC of different shapes. They are connected at the bottom by horizontal pipe. On filling with water, the level in three vessels is same, though they hold different amounts of water. This is so because water at the bottom has the same pressure below each section of the vessel. Because of the same pressure, the pressure difference will be same. Okay, let's see an example. What is the pressure on a swimmer 10 meter below the surface of a lake? Answer: height is 10, density is 1000 kg per meter cube, g we can take it as 10 meter per second square. We already have the formula. P is equals to Pa plus rho Gh because the lake is exposed to the atmosphere. Substituting the values, we will get as 2 atm. There is a 100% increase in pressure from surface level at a depth of 1 kilometer. The increase in pressure is 100 atm. Submarines are designed to withstand such enormous pressures. Okay, they gave extra information as well. If at 10 meters it is 1 atm or 2 atm or 100% increase in pressure, but if we go 1 kilometer down, that is 100 times the depth, then the increase in pressure is also 100 atm, that is 100 atm is the pressure, so many times increase. And submarines which are designed to withstand such enormous pressure. Atmospheric pressure and gauge pressure. The pressure of the atmosphere at any point is equal to the weight of a column of air of unit cross-sectional area extending from the point to the top of the atmosphere. Okay, the pressure of atmosphere at any point is equal to the weight of column of air of unit cross-sectional area extending from that point to the top of the atmosphere. Okay, at sea level, it is 10 power 5 Pascal, 1.013 into 10 power 5 Pascal, which is considered as 1 atm. 1 atm, Italian scientist Evangelista Torricelli, 1608 to 1647, devised for the first time a method for measuring atmospheric pressure. A long glass tube closed at one end and filled with mercury is inverted into a trough of mercury as shown in figure 10.5a. Let's see the figure 10.5a. The mercury barometer. This is called as a mercury barometer. This is basically a glass tube, a glass kind of a test tube, but very long. This is a long glass test tube, and this is a trough of mercury, basically a beaker or a substance that is or a container that is containing mercury. Now, when we place this glass test tube inside this trough of mercury, we can observe that the mercury will rise to a certain height, till a certain height. This height, let's read first. In this figure, this device is known as a mercury barometer. The space above the mercury column, the test tube contains only mercury vapor whose pressure P is so small that it may be neglected. Thus, the pressure at point A, which is equals to 0, the pressure inside the column at point B must be the same as the pressure at point C, which is atmospheric pressure PA. The pressure at point B, okay, let's read more. PA, which is equals to rho GH, where rho is the density of mercury and H is the height of mercury column in the tube. In the expression, it is found that the mercury column in the barometer has a height of about 76 centimeter at sea level, equivalent to 1 atmosphere. This can also be obtained using the value of rho in equation 10.8, a common way of stating pressure in terms of centimeter or millimeter of mercury Hg. A pressure equivalent of 1 mm is called as torr, based on after Torricelli. 1 torr, which is equals to 133 PA, that is Pascal. The mm of Hg and torr are used in medicine and physiology. In meteorology, a common unit is the bar and millibar. 1 bar, which is equals to 10 power 5 Pascal, or approximately equal to 1 bar, which is equals to 180. An open tube manometer is a useful instrument for measuring pressure differences. It consists of a U tube containing a suitable liquid, that is a low density liquid such as oil, for measuring small pressure differences, and high density liquid such as mercury for large pressure differences. One end of the tube is open in the atmosphere and the other end is connected to the system whose pressure we want to measure. The pressure P is equal to pressure at point B. What we normally measure is the gauge pressure, which is P minus PA, given by equation 10.8, and is proportional to the manometer at height h. Okay.